In this section, I'll be introducing a number of functions that are of fundamental importance in the study of signals and systems. These functions include the complex exponential functions, the Dirac delta function, and others. The first type of function that I need to introduce is what is known as a real sinusoidal function. So a real sinusoidal function is a function that has this particular form here, where the constants a, omega, and theta are real constants. And such a function has the fundamental period 2 pi over the absolute value of omega and the corresponding fundamental frequency magnitude of omega. And at the bottom of this slide we have a plot of an example of a real sinusoidal function. The next type of function that I need to introduce is what is known as a complex exponential function. So a complex exponential function is a function that has this form, where a and lambda are complex constants. Now a complex exponential can exhibit one of a number of different types of behaviors depending on how the constants a and lambda are chosen. For example, as special cases, complex exponentials include real exponential functions as well as complex sinusoidal functions. The first special case of complex exponentials that I'd like to consider is what are known as real exponential functions. So a real exponential function is a special case of a complex exponential, in other words a function of this form, where the constants a and lambda are restricted to being real numbers. Now a real exponential can exhibit one of 3 different types of behavior depending on the value of lambda, in particular depending on whether lambda is greater than 0, less than 0, or equal to 0. In the case that lambda is greater than 0, x of t increases exponentially as t increases. In other words, we have what's called a growing exponential. An example of a growing exponential is shown in the figure in the bottom left. The second possibility is that lambda is less than 0, in which case x of t decreases exponentially as t increases. This is what's known as a decaying exponential, and this corresponds to the figure shown in the bottom right. And then the last possibility is that lambda is equal to 0, in which case x of t is simply a constant a, in which case we have a figure or a graph like what's shown in the middle here. The second case of complex exponentials that I'd like to consider is what are known as complex sinusoidal functions. So a complex sinusoidal function is a complex exponential, in other words a function of this form, where the constant a is complex and the constant lambda is purely imaginary. In other words, a complex sinusoidal function is a function that has this general form, where a is complex and omega is real. Now by expressing the constant a in polar form, in other words writing it this way, and using Euler's relation, we can always rewrite a complex sinusoidal function so that it has the form that's shown here, where we can write the real part and the imaginary part separately from one another. And what you'll notice here is the real part and imaginary part of a complex sinusoid are essentially the same except for a time shift, because a cosine function and a sine function are essentially the same except one is shifted with respect to the other. A complex sinusoidal function is periodic with fundamental period 2 pi over the absolute value of omega, and the fundamental frequency is the absolute value of omega. On this slide we have an example where the real and imaginary parts of a complex sinusoid have been plotted on separate graphs. And as I was saying on the previous slide, the real and imaginary parts of a complex sinusoid are identical except for a time shift. In other words, this graph on the right here is identical to the graph on the left. The only difference is there's a time shift. One is shifted with respect to the other. On this slide we have plots of 2 different complex sinusoidal functions, in other words functions that have this form e to the j omega t. In one case omega is chosen to be plus 2 pi, and in the other case omega is chosen to be minus 2 pi. And on these plots we've plotted both the real and imaginary part on the same plot, so for this reason we need a 3-dimensional plot. One axis represents the independent variable, which is denoted t here. The other 2 axes are used to represent the value of the complex sinusoidal function. One axis is for the real part and the other axis is for the imaginary part. And when we plot this function, what we end up with is a helical shape, in other words a helix or corkscrew kind of shape. In one case we get a right-handed helix, in the other case we get a left-handed helix. In other words, the helixes are kind of corkscrewing in opposite directions. One is turning counterclockwise, one is turning clockwise. Lastly, I'd like to consider the most general case of a complex exponential function. In other words, I'd like to consider a function of this form where the constants a and lambda are both complex. So if we take the constant a and rewrite it in polar form, and take lambda and rewrite it in Cartesian form, so in other words theta, sigma, and omega are all real constants, and then we use Euler's relation, we can rewrite a complex exponential function in the form that's shown here, where we have the real part and imaginary part sort of separated from one another. And we can make a few observations. In particular, if we look at the real part of this complex exponential function, the real part is essentially a real exponential, this portion here that's highlighted, times a real sinusoidal function, which is this part here. And similarly, if we look at the imaginary part of a complex exponential function, the imaginary part is also the product of a real exponential, this part that I've highlighted here, times a real sinusoidal function, this part here. Now, complex exponential functions have one of three different types of behavior that they can exhibit depending on the value of sigma. If sigma is equal to 0, then the real part and imaginary parts of the complex exponential are both real sinusoids. In the case that sigma is greater than 0, the real and imaginary parts of the complex exponential are the product of a real sinusoid and a growing real exponential function. And lastly, if sigma is less than 0, the real part and imaginary parts of the complex exponential are each the product of a real sinusoid and a decaying real exponential. On this slide, we have some figures to help illustrate the different types of behavior that are exhibited by complex exponentials, depending on the value of sigma, whether it's greater than 0, equal to 0, or less than 0. So in the case that sigma is greater than 0, each of the real and imaginary parts of a complex exponential have the general form that's shown in this figure. In other words, you have a real exponential function that's growing over time multiplied by a real sinusoid. In the case that sigma is equal to 0, you simply have a real sinusoid, and in the case that sigma is less than 0, you have a real sinusoid times a decaying real exponential function. The next function that I need to introduce is known as the unit step function, sometimes called the Heaviside function. It's denoted by the lowercase letter u, and it's defined by this equation here. You can see the function is a very simple function. It's either equal to 0 or it's equal to 1. It takes on no other values. The graph of the function is shown at the bottom of this slide. And the function kind of looks like a step in a staircase, and the height of this step is 1. So this is where the name unit step comes from. Unit basically means 1, so it's a step of height 1, so we call it unit step, a unit step function. You'll notice that there's a discontinuity in this function at the origin. In other words, at t equal to 0. There's a number of different conventions that are followed for what value to assign to this function at the origin. Some people use the value of the left limit at this discontinuity, in other words, a value of 0. Some people use the right limit, in other words, a value of 1. Other people try to be more democratic and use the average of 0 and 1, in other words, 1/2. In a practical sense, it really doesn't matter very much for details in the underlying math that get rather technical and are not worth going into here. The convention that's followed here, though, is we use a value of 1 at the origin, but in some sense it really doesn't matter very much. The next function that I need to introduce is what is known as the Signum Function, which is denoted by SGN. And this function essentially returns the arithmetic sign of a number. So if we give a value t, which is a real number, to the Signum Function, if t is greater than 0, it gives us 1. If t is equal to 0, it gives us 0. And if t is less than 0, it gives us -1. So essentially this is just giving the arithmetic sign of a number, whether it's positive, negative, or 0. And a plot of this function is shown at the bottom of the slide. Again, it's a very simple function. It only takes on 3 different values, +1, -1, and 0. The next function I need to introduce is what's known as the rectangular function, sometimes also called the unit rectangular pulse function. It's denoted by rect, and it's given by this equation here. And you can see this is a very simple function because it only ever takes on the values 0 and 1. It never takes on any other values. A graph of the function is shown at the bottom of the slide, and essentially it's just a rectangular pulse, as the name suggests. The width of the pulse is 1, and then the height of the pulse is 1. You can also see from the graph of the function that it has two discontinuities, one at -1/2 and one at +1/2. Now it turns out, for rather technical reasons which are not worth going into here, that it doesn't really matter what value you assign to this function at the points of discontinuity. The convention that I follow here is when t is equal to -1/2, I assign the value 1 to the function, and when t is equal to +1/2, I assign the value 0. But other textbooks follow differing conventions, and again, it really doesn't matter very much which value is assigned for rather technical reasons that are not worth going into here. The next function that I need to introduce is known as the Cardinal Sine Function, sometimes just called the sinc function. It's denoted by the letters sinc. This is why we sometimes refer to the function as the sinc function. This is how we write it mathematically. And it's defined by this equation here. In other words, the sinc of t is defined to be sine of t over t. And I just want to take a moment to point out that sinc of 0 is well defined. It's not an undefined quantity. Because you might say when you evaluate this function at t equal to 0 that you get division by 0, therefore the function is undefined, but this logic is flawed because not only does the denominator become 0 when you let t equal to 0, but the numerator also becomes 0 as well. So you end up with something that looks like 0 over 0, which is what we call an indeterminate form. And if you remember from calculus, if you have something that has the form 0 over 0 and you want to figure out what value it actually has, use something called L'Hopital's rule. And if we apply L'Hopital's rule, it turns out that what we end up with is the well-defined value of 1 for sinc of 0. A plot of the sinc function is shown at the bottom of this slide. This function keeps oscillating forever, so although I've only plotted the graph between -10 pi and +10 pi, the function doesn't stop oscillating at plus and minus 10 pi. It keeps oscillating forever to plus and minus infinity. The oscillations get smaller and smaller, but they don't completely stop until you get all the way to plus and minus infinity. Now it might seem that this is the most useless function that you've ever seen in your life, and there could not be any possible use for it in any sort of way, but it turns out that this is probably one of the single most important functions in all of engineering, for reasons that are not at all obvious, but we'll find out later in the course why this particular function is so extremely important. But for the time being, you'll just have to sort of take it on faith that it actually is important. The next function that I need to introduce is what's known as the unit impulse function, sometimes also called the Dirac delta function or the delta function, also sometimes called the impulse function. It's denoted by the Greek letter delta. This is the lowercase letter delta in the Greek alphabet. And the delta function is defined by essentially two properties. The first property is the function is 0 everywhere except at the origin. And the second property is if you integrate this function over the entire real line, the result you get is 1. In other words, the area under this curve is equal to 1. Now technically the delta function is not a function in the ordinary sense. It's what we refer to as a generalized function, and this is one of the reasons why the function is sort of defined in a different way from how you're accustomed to probably defining functions. Normally the way we define a function is we give formulas that specify for like every place in the domain of the function what its value is equal to. Instead what we do here is we specify only what the function is equal to over part of its domain. In particular, for all t not equal to 0, we say what the function is equal to, but we very carefully avoid saying what the function is actually equal to at the origin. And the reason for this is if you think about what these two properties together imply, they imply that the delta function must be infinite at the origin. Because essentially because the function is equal to 0 everywhere except at the origin, if you wanted to compute the area under this curve, essentially the area under this curve is going to be the area of a rectangle where the width of the rectangle is 0 and the height of the rectangle is the value of the delta function at the origin. And because 0 times any finite number is equal to 0, and because the area of the curve under this curve is 1, this implies that the value of the function at the origin must be infinite. And 0 times infinity is what we call an indeterminate form, it can equal potentially any value depending on at what rate the value is going to 0 and the value involved is going to infinity. You might just ask, well, if the value of the delta function is infinity at the origin, why don't we just define it saying that when t is equal to 0, the delta function is equal to infinity? The problem with this is that infinity is not a number. It's just the concept of something being arbitrarily large. And essentially, some infinities are bigger than others. Not all infinities are equally infinite. So it would be ambiguous to specify the delta function as being equal to infinity at the origin, because infinity, there's different levels of infinity, and how infinite do we really mean? So instead what we do is we define, kind of implicitly define what the function is equal to at the origin by specifying this second property of the delta function. And essentially what we're doing here is we're saying the delta function is just the right level of infinity at the origin, such that when you integrate this function, the result that you get is equal to 1. In terms of graphs, the way that we graphically denote the delta function is using a notation like this. Because the delta function is equal to an infinite value, we don't try to draw a point on the vertical axis at infinity, because that would really mess up the scale of our graphs. Instead, what we do is just draw an arrow pointing upward, meaning that the value is infinite, and we put a number next to the arrowhead indicating what's the constant multiplying the delta function. In other words, are we plotting, in this particular case, we're plotting 1 times the delta function. So this is indicating, the graph is indicating 1 times delta. If instead we were plotting 5 times delta, for example, if this was 5 delta here, then we would put a 5 here. The reason we have to make this distinction is, again, not all levels of infinity are equal. 5 times the delta function is 5 times as infinite as just the delta function. So it makes a difference in the mathematics if you multiply a delta function by a constant. It's no longer the same function. It's a scaled version. And on the graph at the right here, we're just showing a delta function that's been shifted by t0 and scaled by a factor of k. So if it's shifted by t0, it's going to be shifted horizontally by amount of t0. In this particular case, t0 must be positive. And k is just indicating the weight that's attached to the delta function. The delta function has been scaled by a factor of k, so the way we denote this is putting a k next to the arrowhead here. On the previous slide, we were introduced to the delta function, and if you recall, one of the defining properties of the delta function is that if you integrate the delta function over the entire real line, the result that you obtain is 1. And what I want to do now is I want to try to explain on this slide how it's possible that such a strange and unusual function as the delta function can have such a well-defined value of 1 for its integral. So in order to do this, what I'm going to do is I'm going to define a function which I'm denoting by g subscript epsilon, which is given by this formula here. And probably rather than looking at the formula, it's more helpful to look at a graph of this function, so I have the function plotted just below here. So what we have essentially is a rectangular pulse where the width of the pulse is epsilon, because it's non-zero between minus epsilon over 2 and epsilon over 2, so the length of this interval is epsilon. And the height of this pulse is 1 over epsilon. So I hope everyone would agree with me that the area of this function, no matter how I choose epsilon, is precisely 1. Because essentially what we have here is the area of a rectangle where the width of the rectangle is epsilon, and the height of the rectangle is 1 over epsilon, and 1 over epsilon times epsilon is 1. Now if you want to have a good mental model for what the delta function is, imagine taking the limit of this function g subscript epsilon as epsilon goes to 0. So as epsilon goes to 0, what's going to happen to this function here? Well, as epsilon goes to 0, the width of this rectangular pulse is going to become narrower and narrower and narrower. And the height of the pulse is going to become taller and taller and taller, because as epsilon goes to 0, 1 over epsilon goes to infinity. So as epsilon's going to 0, the pulse gets narrower and narrower and taller and taller. And essentially what the delta function is the limiting case where epsilon actually, we take the limit when epsilon goes to 0, in which case the pulse becomes infinitely high, like infinitely tall, and infinitely narrow. It just basically shrinks down to a width of just a single point. So again, if you want a good mental model or mental picture for how to understand how it's possible that the delta function has this very well-defined area of 1 underneath it, essentially this is a good way to think of it in terms of this limiting case of a rectangular pulse. As it turns out, the delta function plays a critical role in the context of signals and systems. So often for this reason we'll find ourselves manipulating mathematical expressions that contain delta functions. So for this reason it's helpful to know some of the properties that the delta function possesses, because this will make it easier for us to manipulate expressions that contain delta functions. So there's two properties I need to introduce on this slide. The first of these properties is what's known as the equivalence property. And what it says is for any continuous function x and any real constant t0, the following identity, this one here, holds. And if you compare the left and right hand side of this equation, the only difference is on the left hand side we have a t, and on the right hand side we have a t0. So effectively what this is saying is we can change this t on the left hand side to a t0, or vice versa. It makes no difference because the left and right hand side are equal. The second property I need to introduce is what's known as the shifting property, and what it says is for any continuous function x and any real constant t0, a relationship of this form is satisfied. So effectively what this relationship is saying is that if I have some arbitrary function x that's continuous, that's multiplied by a shifted delta function, this is basically a time shifted delta function because of this minus t0 here, and then we integrate the result over the entire real line. This whole integral here simply simplifies to the function that's multiplying the delta function evaluated at the point where the delta function is non-zero. In other words, evaluated at t0, because this right hand side is x of t0. The place where the delta function is non-zero is t0, because the delta function is 0 everywhere except at the origin. So if we take the delta function and we shift it by t0, the shifted delta function that appears here will be 0 everywhere except at t0. At this point I'd like to consider a few examples that illustrate the use of the equivalence property and shifting property, but just before I do this I'd like to show a figure which illustrates the graphical interpretation of the equivalence property. On this slide I have a few figures to help illustrate the equivalence property in graphical form. So to begin with, we have some arbitrary continuous function x. In this case I've drawn a triangular pulse, but you can imagine any arbitrary continuous function appearing on this graph. Then we have a shifted delta function that's been shifted by t0. So the graph of this function is going to look like what's shown here, where the delta function has been shifted by t0. So the place where this shifted delta function is non-zero is going to be at t0. And then if we graphically multiply these two functions together, which is what's shown in the bottom graph, it's the product of the two functions at the top, because this second function, the delta of t minus t0, is equal to 0 everywhere except at t0, when we multiply x times this function, the answer we get will be 0 everywhere except at t0. And at t0, the particular value we're going to get is this shifted delta function times the value of the function x at t0. In other words, this value here, x of t0. In other words, we're going to get x of t0 times this delta function here. But if we compare this expression here, which is what the graph is plotting, with what we actually have appearing on the graph, what we actually have appearing on the graph is delta of t minus t0, this highlighted expression, times x of t0. But this is equal to what the graph is actually plotting, which is x of t times delta of t minus t0. Therefore, these quantities are equal. In other words, the equivalence property holds. So essentially, the equivalence property follows directly from the fact that the delta function is non-zero only at the origin and it's 0 everywhere else. So now moving on to the examples, the first example I'd like to go through is example 3.8. In this example, we're given this integral that's shown here, and we're asked to evaluate it. So the first observation we can make is the integral that we're dealing with here has the form of what's specified in the shifting property. In other words, what we have here is some arbitrary continuous function, in this case it's sine of t, multiplying a shifted delta function, which in this case is shifted by pi by 4. And then we're integrating over the whole real line. So this integral here has the form of the integral that appears in the sifting property. So we can use the sifting property to evaluate this integral. And the sifting property is essentially this formula here that's written below. So putting the integral that we're given in the context of this formula here, the x of t that appears in this formula here corresponds to the sine of t here. So our function x is the sine function. And the t naught that appears in this formula here would correspond to pi by 4. This is the amount the delta function's been shifted by. So the sifting property tells us this whole integral should evaluate to just the function x, which in this case is the sine function, evaluated at t naught, which in this case is pi by 4. So we're just going to get sine of pi by 4, which if you happen to recall is 1 over root 2. The next example I'd like to consider is example 3.9. In this example, we're given this particular integral here, and we're asked to evaluate it. In other words, fully simplify the integral. So the first observation we can make is that the integrand contains a delta function, right here. So some of the properties of the delta function that we were introduced to earlier, namely the equivalence property and sifting property, might potentially be of use to us. Now, we can't quite use the sifting property for the integral as it's stated here. The reason why is, if you recall, the sifting property, which is shown down below here, it involves a delta function that's only been shifted. So we have here tau minus t naught. So this delta function's only been shifted. There's no time scaling operation being applied to the delta function. If we look at the integral that we're given here, because of the constant 4 that appears here, there's actually a time scaling operation being applied to the delta function in addition to the time shift that's associated with this constant 1. So because of this, we can't directly apply the sifting property because the integral that we're dealing with here doesn't quite match the form of the sifting property integral. But we can fix this problem relatively easily by using a change of variable. So what I'm going to do is I'm going to define a new variable, which I'm calling tau here, and I'm going to define it to be equal to 4t. And the motivation for this definition is I want it to be such that after I apply the change of variable, this constant 4 disappears. And effectively what I've done here is I've absorbed the constant 4 into the definition of tau. So after I do the change of variable, the 4 will be gone. So if tau is defined to be equal to 4t, in other words we have this relationship here, then we can rearrange and solve for t in terms of tau. We get t is equal to tau over 4. And we can also take derivatives. We get dt is equal to d tau over 4. And then we can apply a change of variable. We can rewrite all of the t's on this side of the equation here with tau's on this side of the equation. And going from this line to the next line, all we've done is we just simplified. We have 2 over 4 here. We can write this as just 1 over 2 in this fraction that appears here. And now at this point we can use the sifting property, because now the thing that appears in the integrand that involves the delta function, this is strictly a shifted delta function. It's shifted by 1 unit, but there is no scale factor in front of the tau now. So it's strictly just a time shift. So everything else matches the form of the sifting property integral. We have a time shifted delta function here. We have some arbitrary function out front that's multiplying the shifted delta function. And then we're integrating from minus infinity to infinity. So it matches the form of this integral down here. So we can apply the sifting property. And when we do this, what's going to happen is the result of this integration here is simply going to be the function in square brackets here, the thing that's multiplying the shifted delta function, evaluated at the value of tau, where this delta function is non-zero. And because this delta function has been shifted by 1 unit, it's going to be non-zero at tau equal to 1. Therefore, we're going to evaluate this quantity in square brackets at tau equal to 1. In other words, we have this next line here. And if we evaluate this expression at tau equal to 1, this gives us the next line. And then sine of pi by 2 is just 1. So we're going to have 1/4 times 1, which is equal to 1/4. And that's our final answer. Finally, the last example that I'd like to go through is example 3.10. In this example, we're asked to evaluate this particular integral here. In other words, we want to fully simplify the integral. So the first observation we can make is the integrand contains a delta function. So because of this, the properties of the delta function that we discussed earlier might be helpful. We talked about the equivalence property, and we also talked about the sifting property. In this particular example, the sifting property is not directly useful because the upper limit of the integral here is not positive infinity. So this integral doesn't match the form of what the sifting property allows us to deal with. On the other hand, the equivalence property is something that could be applied here, because in the integrand here what we have is a shifted delta function, delta of tau minus 2, multiplying some other function, this tau squared plus 1. And this matches the form of the expression that the equivalence property allows us to deal with. So let's try applying the equivalence property. Maybe we might be able to simplify things at least a little bit. So we're going to apply the equivalence property to the integrand here. So what the equivalence property says is that if we have some arbitrary function multiplying a shifted delta function, so our arbitrary function in this case is tau squared plus 1, multiplying the shifted delta function, what the equivalence property says is the result of this is equal to the shifted delta function times this expression, the thing that's multiplying the shifted delta function, evaluated for the value of tau, where this delta function, the shifted delta function, is non-zero. And since this delta function has been shifted by 2 units, it's going to be non-zero at tau equal to 2. Therefore, the equivalence property says that this whole expression here can be replaced by delta of tau minus 2 times this expression evaluated at tau equal to 2. So we're going to replace this highlighted expression by its value when we evaluate it at tau equal to 2, which just gives us 2 squared plus 1. And 2 squared plus 1, of course, is 5, so we can factor the 5 out of the integral. So we've managed to simplify the problem somewhat. We've gone from this integral here that we started out with to a slightly more simplified result. But still, we can't use the sifting property to simplify this integral that we have here because the upper limit of integration is not positive infinity. Now, unfortunately, a change of variable won't help us here because no matter how we try to apply a change of variable, we're going to end up with one of the two limits being wrong, or at least one of the two limits. So we're going to have to apply some kind of other logic or reasoning process here in order to simplify this integral further. So the logic that we're going to use here is what's shown in this diagram off to the side. So I'm going to focus on just evaluating this integral that I have underlined here. In other words, this integral on the left-hand side of this equation here. And the claim that I make is this integral is equal to this expression here, which is just a unit step function that's been shifted by 2 units to the right. But where does this result come from? So if we look at this figure off to the side here, the function that we're actually integrating is a function that looks like what's plotted here. We have a delta function that's been shifted by 2 units, so we have this spike up to infinity at tau equal to 2, and everywhere else the function we're integrating is 0. So if we're integrating a function that looks like this, as long as we don't include 2, tau equal to 2, in the interval that we're integrating over, the result is going to be 0 because we're effectively integrating a function that is 0 everywhere where we're integrating it. The only way that we can get a non-zero result is if the interval that we're integrating over includes the value tau equal to 2. So this is the reason why when t is less than 2 the result we get is 0, because when t is less than 2 it means that this point here, the upper end of our interval we're integrating over, is somewhere to the left of 2. Therefore, 2 is not included in the interval we're integrating over. Therefore, we're integrating a function that's always 0. Therefore, the result is 0. On the other hand, if t is greater or equal to 2, in other words, this point here either comes up to 2 and touches it or goes past 2, then we're going to be including this point in the interval we're integrating over, which means whatever area there is associated with the point tau equal to 2 will get picked up. And the claim I make is the area that's going to get picked up at tau equal to 2 will be an area of 1. And this is what leads to the result that the answer of the integration is 1 when t is greater or equal to 2. But why is the area equal to 1 in this case? For this, I need to come down to this figure here. So suppose you're integrating a delta function. If you're integrating a delta function and you integrate it over any interval which includes the point where the delta function has its spike up to infinity, the answer you're going to get will be 1. Because we know that the defining property of the delta function says that if you integrate this function over the entire real line, you get 1. So we know overall the area under this curve is 1. But we also know the function is 0 everywhere except at a single point, which is this point here. Therefore, we can reason that this implies that all of the area of 1 under this curve is all concentrated at the point where the delta function is non-zero. So if we're integrating a delta function, we can only get one of two answers. Either we get 1 or we get 0. And the specific circumstance under which we'll get 1 is if this point where the delta function is non-zero is in the interval that we're integrating over, in which case all of the area under this function, which is concentrated at this point where the delta function is non-zero, which is an area of 1, will get picked up, giving us an answer of 1. Otherwise we get an answer of 0. So if we go back to this figure over here, the reason why when t is greater or equal to 2 we get an answer of 1 for the integral is because in this case we're going to pick up all of the area that's concentrated at the point tau equal to 2, which is an area of 1, which leads to this result here, 1 when t is greater or equal to 2. And once we have this result, you can make the observation that this multi-case expression here with two cases, one for t greater or equal to 2 and one for t less than 2, these cases can be collapsed together and simply written in terms of a unit step function as unit step function that's been shifted 2 units to the right. And then we can take this expression here and we can plug it into this underlined expression from above, because effectively we've computed this underlined integral here. It's u of t minus 2, so we can plug this in here, which gives us our final answer. At this point, I'd like to consider representing a rectangular pulse using unit step functions. So to make this more concrete, let's let a and b denote two real constants, where a is less than or equal to b. And let's consider a function x of the following form, a function x which is given by this equation here. So this is a function that is expressed in terms of two cases. If t lies between a and b, the function is 1, otherwise it's 0. This function x corresponds to a rectangular pulse where the height of the pulse is 1 and the rising edge is at a and the falling edge is at b. It turns out that the function x can also be equivalently written using an expression of this form that I've highlighted here. In other words, it can be represented as the difference between two time-shifted unit step functions. Now this is a very helpful thing because the advantage that this expression here has over the one at the top of the slide that we originally have for our function x is that this particular expression here is a single expression, like a single case, that's valid for all t. Whereas the formula that we have up here consists of two cases. So if you imagine that you're substituting this function x into a number of places in some larger problem that you're trying to solve, every time you substitute for x you have to ask the question, is t between a and b, or is it the otherwise case that applies? Otherwise you don't know whether you need to substitute 1 for x or substitute 0. So it's a little bit of a headache having multiple cases like this, because you always have to do additional bookkeeping to keep track of, well, which case applies, and then you know which value to substitute. On the other hand, this expression here is a single case that's valid for all t. So if you were substituting this expression into some bigger problem, you don't have to worry about what is t equal to, because this equation or this expression always applies regardless of what t is. So in effect, what the unit step function has allowed us to achieve here is has allowed us to take a function that's expressed in terms of a number of cases, in this case 2 cases, and rewrite it as a single expression that's valid everywhere. In other words, we've collapsed 2 cases into a single case, and this can often be quite helpful to do. At this point, I'd like to consider an example. In particular, I'd like to do example 3.11. In this example, we're asked to show that the rect function, in other words the rectangular function, can be expressed in terms of a pair of time-shifted unit step functions in the way that I've highlighted here. Before we start this problem though, just recall that the unit step function looks something like this. The formula for the unit step function is given here. If we plot this function, it has the form that's shown here. In other words, it's 0 for negative t and 1 otherwise. So getting back to the problem at hand, what we want to do is we want to write expressions for each of these individual terms, for u of t plus 1/2 and for u of t minus 1/2. So let's focus on the first term first. So u of t plus 1/2, this corresponds to a unit step function that's been shifted by minus 1/2 units. The reason why is with time shifts we have to interpret the time shift with a minus sign. In other words, it's t minus something. So this would be t minus minus 1/2. So we're shifting by minus 1/2, which means that we're going to take this function here, u of t, and it's going to get shifted 1/2 unit to the left. In other words, 1/2 unit in the negative direction, which will give us the function that's shown in this graph. Then if we focus on the second term here, the u of t minus 1/2, this particular expression here corresponds to a unit step function that's been shifted 1/2 unit to the right. In other words, shifted by positive 1/2. So again, we're going to take this function that's shown in the graph at the bottom here, u of t, and we're going to shift it 1/2 unit to the right, which will give us this function here. So this is the function u of t minus 1/2. So from these two graphs here, we can very easily write expressions for u of t plus 1 and u of t minus 1. And then what we do next is now we're going to basically take the difference between these two terms, because what we want is the difference between this term here and this term here. So if we combine these together and take the difference, what we have essentially is three cases. Either the case that t is less than minus 1/2, t is between minus 1/2 and plus 1/2, or t is greater than 1/2. In the first case, what we end up with is this first expression is equal to 0 when t is less than minus 1/2. And the second term here is equal to 0 as well. So we get 0 minus 0, which is just equal to 0. So that's where this first case here is coming from, where it's 0. Then if we go on to the case that t is between minus 1/2 and plus 1/2, in this case, when t is between minus 1/2 and plus 1/2, this term here is equal to 1, and this term here is equal to 0. So we get 1 minus 0, which simplifies to 1. So the second case here is equal to 1. And then the last case, when t is greater than 1/2, what we end up with is this term here is equal to 1, and this term here is equal to 1 as well. So we get 1 minus 1, which is equal to 0, which gives us this case here. This case here. So we can kind of collapse two of these cases together just by observing that the function is equal to 1 in this case, where t is between minus 1/2 and plus 1/2, and it's 0 otherwise. So we can just collapse this down to two cases. And this is just the definition of the rectangular pulse. The rectangular pulse is equal to 1 between plus and minus 1/2, and it's 0 otherwise. In other words, we have this function here, which is just the rectangular pulse function. On the previous slide, we saw how we could exploit unit step functions in order to take a formula for a rectangular pulse that consists of two cases and collapse it into a single case. Now the idea from the previous slide can be extended to handle any function that's defined in a piecewise manner. In other words, a function that consists of a number of different cases. And this is often a helpful thing to do because, again, having an expression that's valid for all cases, a single case in other words, is very advantageous, because if you're needing to substitute an expression in many different places, it's very painful if it consists of multiple cases, because you always have to worry about which is the appropriate case to substitute. Whereas if you have an expression that only consists of a single case and you need to substitute that expression in a number of places, you don't have to worry about which case applies because there's only one. At this point, I'd like to consider an example, and in particular, I'd like to consider example 3.12. In this example, we're given a function x that's defined by the equation that's specified here. And you'll notice this equation consists of a number of cases. In other words, the value of x of t depends on the specific range that t falls in. If it's between 0 and 1, we get t. If it's between 1 and 2, we get 1. If it's between 2 and 3, we get 3 minus t, and we get 0 otherwise. So essentially we have a an expression for the function, or the value of x of t, that consists of 4 cases. And what we're asked to do in this particular example is find a single expression for x of t that's valid for all t. In other words, it consists of only a single case, and it's valid for all t. And the approach that we're going to use to do this is we're going to use unit step functions and rectangular pulses. So to begin with, what I'm going to do is I'm just going to plot the function x of t to give us a little bit more insight into what the graph looks like. So this graph is plotted down below in figure A. So if you ignore all the color annotations that I've added and just focus on the original graph, which is in black, the graph that appears here, the line that's plotted in black, is the function x. Now I hope everyone would agree with me that if I add the functions v1, v2, and v3 that are shown in figures B, C, and D respectively, that the sum of these 3 functions is the function x. It's relatively easy to add the functions v1, v2, and v3 just doing this visually because these functions are never simultaneously non-zero. So for example, between 0 and 1 of the functions v1 and v2 and v3, the only one of these 3 functions which is non-zero between 0 and 1 is the function v1. And then between 1 and 2, the only one of these 3 functions which is non-zero is the function v2. And then between 2 and 3, the only one of the 3 functions v1, v2, and v3 that's non-zero is the function v3. So because of this, it's very easy to add these graphs. Essentially what you're doing is just taking the 3 graphs and superimposing them on the axes that are shown in figure A. So v1 plus v2 plus v3 gives us the function x. So how does this help us? Well, what we're going to do is for each of the functions v1, v2, and v3, what we're going to do is we're going to write a single expression for the function v1, for example, that consists of only a single case that's valid for all t. And then we're going to do a similar thing for the function v2. We're going to write a single expression that consists of only one case that's valid for all t for the function v2, and then we're going to do a similar thing for the function v3. We're going to write a single expression that consists of only one case that's valid for all t. And if we can do this, then we can simply add the expressions that we get for v1, v2, and v3 to get a formula for the function x that consists of a single case that's valid for all t. So then let's look at how we can write an expression for example, the function v1 that consists of only a single case that's valid for all t. So the observation we can make here is the function v1 is simply the original function x, that's shown in figure A here, multiplied by this rectangular pulse that I've drawn in green, this rectangular pulse function here in green. If I multiply this by my original function x, this will give me the function v1. Now if we stop and think about it, what's the formula for this rectangular pulse that I've sketched in here? Well, it's this formula here that's written in green. We have u of t minus u of t minus 1. So you can read this expression u of t, read this with the t here is a t minus 0. So the significance of the 0 is this is the rising edge of this rectangular pulse. It has a rising edge at 0. The significance of the constant 1 that appears here, this is the falling edge of the rectangular pulse, which is what we have here. This rectangular pulse in green has a falling edge at 1. And then the height of the rectangular pulse is simply 1. So if I multiply this expression here in green times the original function x of t, which is equal to t over this interval between 0 and 1, this gives me the function v1 over here. In other words, what we have is that v1 is equal to t, that corresponds to our original function x, times this rectangular pulse, which is the formula in square brackets. And then we're just going to repeat this process for the graphs of v1 and v2, or sorry, the graphs of v2 and v3. So in the case of the function v2, what we have here is this graph here, or function v2, is given by taking our original function x, the line that's in black here, and multiplying it by this purple colored rectangular pulse in the middle here. If we multiply this purple rectangular pulse times our original function x, this is going to give us this function here, v2. So now we just want to write a formula for this rectangular pulse times our original function x. So the formula for this rectangular pulse, which has a rising edge at 1 and a falling edge at 2, is going to be this expression that's written in purple here, where the significance of this constant 1 that appears here, this t minus 1, the significance of the 1 is this is the rising edge of the position of the rising edge of the rectangular pulse. And the significance of this constant 2 in t minus 2, the 2 is the falling edge of the rectangular pulse. And then the height of the pulse is just 1. So if we take this purple formula here and multiply it by the formula for the function x between 1 and 2, which is just equal to 1, this gives us the formula for the function v2. So in other words, the formula for v2 is given just by 1, which corresponds to the function x, times the quantity in square brackets that I've added here, which is the formula for the rectangular pulse that we're multiplying by. And lastly, in the case of the function v3, the function v3 is obtained by taking this rectangular pulse that's drawn in kind of an orangish color times our original function x. So if we multiply these two things together, this will give us our function v3. And we can easily write a formula for this function v3 by just writing the formula for x multiplied by the formula of this orange expression here. So between 2 and 3, over this interval here, the function x is given by 3 minus t. So the portion of the formula that is the corresponding to x is equal to 3 minus t. And then the rectangular pulse is defined by this expression here in orangish color, u of t minus 2 minus u of t minus 3. The significance of the 2 here, this is where the rising edge of the rectangular pulse is. You can see the rising edge is at 2. And the significance of this 3 here in t minus 3, the 3 is the falling edge of the rectangular pulse, which is at 3. So if I multiply this expression that's in an orangish color times 3 minus t, this gives us the formula for the function v3. In other words, we have this expression here. So now we have a formula for each of v1 and v2 and v3 that each consist of a single case that's valid for all t. So if we add these functions together, v1 plus v2 plus v3, this gives us a formula for x. But notice that the formula that we end up with here consists of just a single case, and that's valid for all t. So this is exactly what we're looking for. Again, in this exercise, what we're trying to do is simply try to find an expression for x that consists of only a single case that's valid for all t. And we've found such an expression now.